Welcome to the Deep Dive. Today we're tackling vaccines, those remarkable biological tools that give us active acquired immunity.
Yeah, a fascinating topic.
We've gone through all the materials you sent over, articles, research, your notes, quite a bit of stuff, actually. And our mission today is, well, to really understand what vaccines are fundamentally, how they work with our immune system, their history, which is pretty amazing, and the different types out there.
Trying to cut through the noise a bit.
Exactly. Cut through any potential overload. And just to start, think about this. Vaccines didn't just control smallpox. They wiped it out globally.
Completely eradicated. It really sets the stage for their potential, doesn't it?
It really does. It underscores what the science says, right? That overwhelming consensus on safety and effectiveness.
Absolutely. They're among the most powerful tools we have against infectious diseases and generally very safe.
Okay, let's get into the mechanics then. How do they actually, work inside us? It feels complex.
Well, essentially, it's a really clever way to educate the immune system.
Educate it?
Yeah. Vaccines introduce something carefully chosen that mimics a disease agent.
Like a look-alike?
Sort of. It could be a weakened microbe, maybe one that's been inactivated or killed, or just a fragment, a piece of a toxin it produces, or maybe a protein from its surface.
But not the actual dangerous disease.
Right. Crucially, it doesn't cause the full disease, but it's enough for the immune system to go, hang on, this is foreign.
Okay.
So the body mounts a defense. It makes antibodies, specialized immune cells, but the real genius part, it remembers.
Creates a memory.
Exactly. The immune system keeps a record of that encounter. So if the real dangerous pathogen ever turns up,
Is ready for it.
it's got the blueprint, it can respond super quickly, neutralize the threat, maybe before you even feel sick, or clear out infected cells much faster, like a training exercise, basically.
That training exercise analogy really helps. So building up internal security that's seen the enemy's tactics.
That's a good way to put it.
Now, I saw distinctions, preventative versus therapeutic. What's that about?
Right. So most vaccines we get, like childhood shots, are prophylactic. Preventative. They stop you from getting sick in the first place.
Standard stuff.
Yeah. But there's this other really exciting area of therapeutic vaccines. These are designed to treat diseases you already have.
Like cancer.
Exactly. Cancer immunotherapy is a big example, trying to get the immune system to attack existing cancer cells. And sometimes vaccines can even achieve what's called sterilizing immunity.
Sterilizing immunity.
Yeah, that's kind of the ultimate goal. It means the vaccine completely prevents any infection, not just symptoms, stops it dead in its tracks.
Wow. Okay. That sounds like the gold standard. But even if they don't achieve that, their impact is still massive.
Oh, undeniably. Vaccination is, hands down, the most effective way we have to prevent infectious diseases. The numbers speak for themselves.
Like the measles example.
Yeah, take measles in the U.S. Before the vaccine, 1958, you had over 763,000 cases. Think about that.
Huge number.
After the vaccine, it dropped to fewer than 150 cases a year. And globally, the measles vaccine prevents something like 1 million deaths every single year.
1 million deaths. That's staggering. And it's not just measles, is it? Polio, tetanus.
Yeah.
Diseases that used to be terrifying.
Exactly. Vaccines have brought them under control in most of the world. It's easy to forget how bad they were. And this protection, it doesn't just help the person who got the shot.
You mean herd immunity?
Precisely. When enough people in a community are vaccinated, the disease just can't spread easily. It hits dead ends.
So it protects people who maybe can't get vaccinated.
Right. People with certain medical conditions, maybe very young infants, or those whose immune systems didn't respond well, they get indirect protection. The polio eradication effort shows this, we're so close.
Just a few places left.
Yeah, parts of Afghanistan, Nigeria, Pakistan. And the challenges there are often things like getting access, sometimes cultural issues, and unfortunately disinformation undermining trust.
It's tough when misinformation gets in the way of something so beneficial. But that herd immunity shield concept is powerful. Oh, and another thing, I saw the link to antibiotic resistance. Didn't immediately connect those two.
It's a really important link, actually, often overlooked. By preventing bacterial infections in the first place, think pneumococcal pneumonia vaccines mean fewer people need antibiotics.
I see.
And using fewer antibiotics helps slow down the rise of those dangerous antibiotic-resistant superbugs. So it's another layer of protection vaccines offer.
Like a preemptive strike on multiple fronts.
Yeah.
Okay, but are they always perfectly effective? Are there limitations? Biology's never 100% right.
You're absolutely right. Nothing's foolproof. There can be what we call vaccine-related failures.
Meaning?
Well, maybe the vaccine itself, like a live attenuated one, didn't trigger a strong enough response, or maybe the schedule wasn't followed properly or it wasn't administered quite right, things like that.
Okay.
And then there are host-related failures. This is where the individual's immune system just doesn't respond adequately.
Why would that happen?
It can affect maybe 2 to 10% of people. It could be down to genetics, their immune status, maybe they're immunocompromised, their age, general health, even nutrition.
So lots of individual factors.
Yeah. There's a specific genetic condition, X-linked agammaglobulinemia, where people just can't make enough antibodies, for example. That's a clear host-related issue.
Really shows how personal our immune systems are. And that protection, it's not instant after the shot, is it?
No, definitely not. It takes time. Your innate system, the first responders, might kick in within, say, 12 hours. But the adaptive response, the bit that makes the specific antibodies and memory cells for long-term protection, that takes maybe 1 to 2 weeks to really ramp up.
So there's a window where you could still get infected.
Exactly, the period of vulnerability. And even when you do make antibodies, how many you make and how well they match the specific strain of the pathogen circulating, that can vary too.
Different strains can be trickier.
Sometimes, yeah. Viruses especially can change, and that might affect how well the vaccine-induced immunity works against them.
So it might not always be complete lifelong immunity. Sometimes it's partial.
That's right. But even partial immunity is really beneficial. It makes it harder to get infected if you are exposed. And if you do get sick, the illness is usually much, much milder.
Lower risk of serious stuff, faster recovery.
Exactly. Lower mortality, less severe disease. We also see something called immunosenescence in older adults.
Immunosenescence?
Yeah, basically, the immune system gets a bit less responsive with age, including to vaccines. That's why some vaccines for older people have adjuvants added.
Adjuvants to boost the response.
Precisely. They help kickstart the immune system a bit more effectively in older individuals. So yeah, overall vaccine efficacy depends on the disease, the vaccine strain, sticking to the schedule, the individual's response, those non-responders and factors like ethnicity, age, genetics.
It's complex.
It is, but it's crucial to remember. Even if someone vaccinated gets a breakthrough infection, it's almost always less severe, and they're less likely to spread it. That's why good modeling, surveillance, and keeping vaccination rates high are so important for programs.
That covers effectiveness really well. Now, the other big topic, safety. Always a major point of discussion.
Indeed. And the key message here, based on vast amounts of data, is that vaccines are generally very safe.
What about side effects?
Most are mild and temporary. Things like a low fever, maybe some soreness or redness where the shot was given, perhaps mild muscle aches, usually just signs the immune system is waking up.
Okay.
Of course, like with any medicine, allergic reactions to ingredients are possible, but rare. And there's a known, very rare link studied between the MMR vaccine and febrile seizures.
Febrile seizures. Sounds scary.
It can be worrying for parents, definitely, but they're typically related to the fever spike and usually don't cause long-term harm.
And do those individual host factors we talked about for effectiveness also affect safety or reactions?
They can play a role. Genetics, overall health, immune status, age, maybe even things like obesity or allergies might influence how someone responds. The elderly or those with allergies might react slightly differently.
But severe reactions are the exception.
Extremely rare, absolutely critical to emphasize that. While there have been, documented very rare complications with specific vaccines like varicella or rotavirus in the past, the safety record for vaccines in routine use is excellent, backed by decades of monitoring.
And I understand there are systems in place if something serious does happen, however rarely.
Yes, that's right. At least 19 countries have set up no-fault compensation programs, like the National Childhood Vaccine Injury Act in the U.S. or the Vaccine Damage Payment in the U.K.
What do they do?
They provide a way to support individuals who experience a severe adverse event determined to be linked to a vaccine without needing to go through long, difficult legal processes to prove fault.
Okay, that's reassuring. So we've got effectiveness, safety. Let's dive into the different types of vaccines. It sounds like there isn't just one way to make them.
Not at all. There's a whole toolkit of strategies all aiming for that same goal: trigger immunity without causing significant illness.
What are some of the main types?
Well, traditionally, you have attenuated vaccines. These use live microorganisms, often viruses that have been weakened in the lab.
Weakened how?
So they can still replicate a bit, enough to alert the immune system, but they don't cause serious disease. Examples are yellow fever, measles, mumps, rubella, the oral typhoid vaccine, BCG for tuberculosis too.
What are the pros and cons?
Big advantage. They often give really strong, long-lasting immunity, hitting both antibody and cellular responses. Downside. Not usually suitable for people with weakened immune systems, and there's an incredibly tiny theoretical risk they could mutate back to a stronger form.
Okay, then what?
Then you have inactivated vaccines, or killed vaccines. Here, the virus or bacteria is completely killed using heat or chemicals.
So no chance of it causing disease.
Right. Zero risk of infection from the vaccine itself. Examples include the injected polio vaccine, IPV, hepatitis A, rabies, and most flu shots.
Makes sense. I also saw toxoid vaccines.
Ah, yes. Toxoids are interesting. Instead of the whole bug, they use an inactivated toxin that the bacterium produces.
The harmful chemical it makes.
Exactly. The toxin is made harmless, but the immune system still learns to recognize and neutralize it. Tetanus and diphtheria shots are classic toxoid vaccines. There's even one for rattlesnake bites in animals.
No way. Okay, what about subunit vaccines? Sounds like using just a piece.
That's precisely it. They use only specific fragments, the antigens that the immune system needs to see, not the whole organism.
I do that.
Can mean fewer side effects sometimes, as you're only including the essential bits. The hepatitis B vaccine uses surface proteins. HPV uses virus-like particles. Some flu vaccines use specific proteins like hemagglutinin. There's even research on making them an edible algae.
Edible algae, wow. Okay, conjugate vaccines, linking things together.
You got it. Some bacteria have this sugary outer coat, a polysaccharide coat. And that coat isn't very good at getting the immune system's attention, especially in infants. So, conjugate vaccines link that polysaccharide to a protein carrier, something the immune system does recognize well.
Tricks the immune system.
Basically, yes. It makes the polysaccharide look more interesting, triggering a much better response. The Hib vaccine, Haemophilus influenza type B, is a major success story for this approach.
Clever. Outer membrane vesicle vaccines, OMVs.
Right. Bacteria naturally shed these little bubbles, or vesicles, from their outer membrane. These OMBs are packed with antigens and are naturally quite good at stimulating immunity.
So scientists just harvest them.
They can, and they can also engineer them to be even more effective. OMV vaccines are used against things like meningitis B.
And heterotypic, using something from another species.
Yes, sometimes called Jennerian, after Edward Jenner. These use a pathogen from a different animal that causes mild or no disease in humans, but triggers immunity to a related human pathogen.
Like Jenner and cowpox for smallpox.
The classic example. A more modern one is the BCG tuberculosis vaccine, which uses Mycobacterium bovis, a cattle bacterium, to protect humans against Mycobacterium tuberculosis.
Fascinating ways to leverage nature. Now, the really modern stuff. Genetic vaccines. RNA, DNA.
Yes, this is a really cutting-edge area. The basic idea is to deliver genetic instructions, DNA or RNA, into our own cells.
And our cells make the vaccine.
Sort of. Our cells use those instructions to produce a specific protein from the pathogen and antigen. The immune system then sees that protein and learns to fight it.
What are the types?
There are viral vector vaccines. They use a harmless virus, like an adenovirus, as a delivery truck to carry the pathogen's gene into our cells.
Okay.
Then there are RNA vaccines, especially mRNA vaccines, which became famous with COVID-19.
Pfizer, Moderna.
Exactly. They deliver the messenger RNA sequence, often wrapped in tiny fat bubbles called lipid nanoparticles. The cells read the mRNA, make the spike protein, and the immune system responds.
And DNA vaccines.
Similar idea, but using a loop of DNA called a plasmid that carries the gene for the antigen. DNA vaccines might stimulate both B and T cells well. They're potentially very stable, no infectious agent involved, and maybe easier to manufacture at scale. The speed we saw with mRNA vaccines during the pandemic was really remarkable, though.
Our bodies become temporary antigen factories. Incredible concept. Are there even more experimental types being worked on?
Oh, absolutely. The field never stops innovating. There's work on dendritic cell vaccines.
What are those?
You take a patient's own dendritic cells, key immune presenters, load them up with antigens in the lab, and put them back in to supercharge the immune response, showing promise for things like brain tumors, melanoma,
Wow.
then recombinant vector vaccines like the Ebola vaccine, RVSVZ-EBO, combining bits of different microbes, T-cell receptor peptide vaccines trying to fine-tune immune responses, targeting bacterial defenses, using bacterial vectors instead of viral ones, antigen-presenting cell
That's
vaccines.
a huge amount of research.
Yeah, and technologies for rapid deployment like virus-like particles or protein nanoparticles. Even things called inverse vaccines trying to calm the immune system for autoimmune diseases. And synthetic vaccines built entirely in the lab from synthetic components.
The future sounds busy.
Okay.
Let's shift slightly. Valence and interactions. Monovalent versus multivalent.
Right, simple distinction. Monovalent or univalent means it protects against just one thing, one antigen, or one strain.
Like a single target vaccine.
Exactly. Multivalent or polyvalent means it protects against two or more. You hear terms like bivalent for 2, trivalent for 3, quadrivalent for 4.
Why choose one over the other?
Sometimes a monovalent shot might be best if you need a really fast, strong response against one specific urgent threat. Combination shots are convenient, though.
And can different vaccines interfere with each other if given together?
Yes, sometimes. Especially with multiple live attenuated vaccines given close together, it's called vaccine interference.
How does that work?
One component might replicate better and kind of suppress the response to the others. The Sabin oral polio vaccine had this issue. They had to carefully balance the different serotypes. It's also been seen with some dengue vaccines.
So designing combinations needs careful balancing. Got it. What about the other stuff in the vial? Beside the main antigen, stabilizers, adjuvants.
Right. It's not just the active ingredient. There are stabilizers to keep the vaccine potent during storage. Adjuvants, as we mentioned, to boost the immune response.
They make it work better.
Yeah. Then you might have tiny residual amounts of things used in manufacturing and activating agents, stuff from cell cultures, maybe trace antibiotics to prevent contamination during production, and preservatives in some, especially multi-dose vials.
To stop bugs growing in the vial once opened.
Exactly. All these are usually in tiny amounts, but important for the vaccine's quality and safety. Allergic reactions are rare, but possible for sensitive individuals.
Let's revisit adjuvants. We mentioned aluminum salts, alum. How common is that?
Very common. Used in tetanus shots, for example. It's thought to create a sort of depot effect at the injection site, releasing the antigen slowly, and also generally stimulates the immune system.
Okay.
And that interesting example from the Gulf War, using the pertussis vaccine itself as an adjuvant for the anthrax vaccine to get a faster response, shows how things can be repurposed.
And preservatives. Thimerosal got a lot of attention. What's the story there?
Right. Preservatives like thiamerosal, phenoxyethanol, formaldehyde were historically vital, especially in multi-dose vials, to prevent bacterial or fungal contamination. There was a tragic incident in the 1920s with contaminated diphtheria vaccine that lacked preservative.
So they were crucial for safety.
Absolutely. Thiamerosal contains mercury, which raised concerns, but huge amounts of scientific study have found no link between thiamerosal and vaccines and autism. Despite that, as a precaution, it's been removed from most childhood vaccines in the US, EU, and other places.
Still used in some flu shots, though.
In some multi-dose vial flea shots in the US, yes. But the shift to single-dose vials has reduced the need for preservatives generally.
Okay. And the other excipients? Aluminum, antibiotics, egg protein.
Right. Aluminum salts are adjuvants. Trace antibiotics prevent bacterial growth during manufacturing. Egg protein is in vaccines like flu and yellow fever because the viruses are grown in eggs.
Ah, now that makes sense.
Formaldehyde is used to inactivate toxins or kill microbes during production. Only tiny traces remain. MSG and 2-phenoxyethanol can be stabilizers. And thiomersal, as discussed, was an antimicrobial.
That clarifies what's actually in the shot. Let's talk names. DTaP, TTaP.
Right.
It looks like alphabet soup sometimes. Is there a system?
Yeah, it can seem that way. There are efforts to standardize, but it's not perfectly global. In the U.S., the CDC works on standard abbreviations.
So DTaP means something specific.
Yes. Diphtheria, tetanus toxoids, and AP is for acellular pertussis, meaning purified parts and not the whole cell.
And
Tetanus and diphtheria toxoids again, but the lowercase d means a reduced dose of diphtheria used for boosters in older kids and adults. The CDC has lists explaining these. There's also the U.S. Adopted Name System, USAN, for more formal names.
Okay, so there is a logic. Now, how did these get approved? The licensing process. Sounds intense.
It is incredibly rigorous. It happens after successful R&D and extensive clinical trials, phase 1, 2, and 3.
What do those trials look at?
Everything. Safety first and foremost. Can it trigger an immune response, immunogenicity? Does it actually prevent the disease effectiveness? And how long does protection last? The safety bar is exceptionally high because they're given to healthy people.
Are there international standards?
Yes, the WHO's Expert Committee on Biological Standardization sets guidelines for manufacturing and quality control, but then national or regional agencies like the EMA in Europe or the FDA in the US do the actual licensing review.
So manufacturers submit all that trial data.
Exactly. A huge package of scientific evidence. The agencies review it all before granting a license to market the vaccine.
And once WHO sets guidelines, each country does its own thing.
Pretty much. Countries adopt or adapt WHO guidelines, and their own regulatory body grants the national license. Overseas deployment, monitoring, public trust, and clear communication are absolutely vital here.
And supply can be limited at first?
Often, yes. Manufacturing takes time to scale up, so countries need plans for who gets the first doses.
Can you tell us a bit more about WHO, EMA, FDA roles?
Sure. WHO does pre-qualification for vaccines used in international programs, like by UNICEF. They check quality, safety, efficacy, manufacturing standards, GMP. They support national agencies but don't usually issue licenses themselves. Some countries rely on EMA or FDA approvals, though those vaccines might be pricier or less suited for local conditions.
And the EU?
The EMA oversees centralized EU-wide licensing, or it can be done nationally. They have detailed scientific guidelines, CHMP, and expert groups for assessment.
And the US FDA?
Similar rigorous process as for drugs. Manufacturers submit a biologics license application, BLA, with all the data. FDA reviews it, inspects manufacturing plants for GMP, approves labeling, and they continue monitoring after licensing.
India has its own system too.
Yes, the CDSCO, led by the Drugs Controller General, handles vaccine licensing there.
And this monitoring continues even after approval. Post-marketing surveillance.
Absolutely crucial. Clinical trials can't find every extremely rare side effect because they don't involve millions of people. So phase 4 studies and reporting systems like V8 in the US keep watch long after a vaccine is licensed.
A continuous safety check. Makes sense. What about scheduling? Why do we get shots at specific ages and boosters?
Schedules are designed for optimal protection. They consider when the immune system is ready, when kids are most vulnerable to certain diseases. Boosters are needed for some vaccines to refresh immunity that might fade over time.
Who decides the schedule?
Globally, the WHO's SAGE group makes recommendations. Countries then adapt them based on local disease patterns, healthcare systems, etc. In the U.S., it's the ACIP committee advising the CDC.
What are the common childhood ones in the U.S.?
Things like hepatitis A and B, polio, MMR, DTaP, Hib, chickenpox, rotavirus flu, meningococcal, pneumococcal. Quite a list.
Must be hard to keep track.
It can be. That's why reminder systems help, and combination vaccines like pentavalent or MMRV reduce the number of actual shots.
And it's not just kids, right? Adults need vaccines too.
Definitely. Boosters for tetanus, maybe measles depending on when you were born, flu shots annually, pneumonia vaccine for older adults, HPV for adolescents, young adults, shingles vaccine later in life. Pregnant women get recommendations too. Schedules can also be adjusted for immunocompromised people or during outbreaks with limited supply.
Tailored strategies. Okay, let's talk money. The economics. It sounds like developing vaccines, especially for poorer countries, isn't always profitable.
That's a major challenge. Vaccines for diseases like HIV, malaria, TB are desperately needed, but primarily affect low-income countries. So the financial incentive for big pharma to invest billions can be, well, limited.
Less return on investment.
Exactly. Even in rich countries, vaccine development is high risk, high cost, long timeline. Returns aren't always massive compared to drugs for chronic conditions.
So how do these important vaccines get made?
A lot relies on push funding. Governments, universities, nonprofits, foundations provide grants and support for the early research and development.
But vaccines save money in the long run, right?
Hugely cost-effective. The public health benefits are enormous. The rise in vaccine use is probably more driven by public health policy and mandates than pure market forces.
What about patents? Are they a big barrier to access, especially in developing nations?
It's complex. WHO suggests the biggest barriers aren't always patents themselves, but the cost and complexity of building manufacturing plants, the infrastructure needed, and the lack of skilled workers.
You can't just make a generic vaccine easily.
No, they're complex biologics. A new facility needs full clinical testing. Specific processes might be patented, but sometimes they can be worked around with R&D. For newer tech like HPV or mRNA vaccines, patents might be more of an issue. We saw that whole debate during COVID about waiving IP rights.
A thorny issue. Okay,
Well,
the actual production, you said it's incredibly rigorous.
Extraordinarily rigorous because you're giving them to millions of healthy people, often kids. The standards are sky high. Facilities cost a fortune, $50 million to $500 million or more. Specialized clean rooms, containment.
And finding people with the right skills is hard.
Yes, there's a global shortage of trained personnel for vaccine manufacturing.
What are the main production steps?
First, antigen generation. Growing the virus, maybe in eggs or cell lines, or bacteria in big bioreactors, or making recombinant proteins in yeast or cells, flu often in eggs, Hep A in human cells, Hep in bioreactors.
And what?
Then isolate the antigen. Might involve inactivating the virus, purifying the protein, then formulation adding the adjuvants, stabilizers, preservatives, and finally, fill and finish. Putting it into vials or syringes, packaging. That last step can be a real bottleneck.
Are production methods changing?
Yes, moving more towards cultured mammalian cells, recombinant DNA tech for safer options like detoxified toxins or subunit vaccines, and designing combination vaccines efficiently is a focus.
Who are the big manufacturers globally?
Dominated by a few large companies, Merck, Sanofi, GSK, Pfizer, Novartis. Most sales were traditionally in the US, but manufacturing capacity is growing significantly in countries like Brazil, China, and especially India.
India is a major player.
Huge. Serum Institute is one of the world's largest producers. China's big too, mostly for domestic needs historically.
Yeah.
Brazil's increasing self-sufficiency.
Let's talk delivery. Mostly injections, right? Any cool alternatives?
Injection is standard, yeah, but lots of research into other ways. Liposomes, ISCOM, special delivery vehicles. Oral vaccines have had success. The oral polio vaccine was revolutionary.
Why was oral polio so good?
Easy to give, no needles, no blood contamination risk. More stable, less need for refrigeration, which is huge in some parts of the world.
What else is being explored?
Microneedles. Tiny needles on a patch, basically painless delivery into the skin, and needle-free patches with microprojections. These might even be more effective by targeting skin immune cells, maybe using less vaccine dose.
Exciting possibilities. What about animals? Veterinary vaccines are important too.
Hugely important for the animal's health, obviously, but also to stop diseases spreading to humans, zoonotic diseases.
So pets and livestock get vaccinated routinely.
Yes. Dogs, cats, cattle, poultry, and sometimes even wildlife, like dropping rabies vaccine baits for raccoons. Dog rabies shots are often legally required.
Can humans get sick from animal vaccines?
Very rarely, but it's been reported usually accidental exposure, maybe through aerosol vaccines used in clinics. Costs can differ too, rabies vaccine for humans versus dogs, for instance.
I saw something called DV vaccines for animals. Differentiation.
Differentiation of infected from vaccinated animals. DIVA, or Merker vaccines.
How do they work?
They're designed so you can tell if an animal's immunity is from the vaccine or from a real infection. The vaccine is missing at least one bit, an epitope, that the wild virus or bacterium has.
And you test for that missing bit.
Exactly. You use a companion diagnostic test that looks for antibodies only to that missing epitope. If the animal has antibodies to the vaccine parts but not the missing bit, it was vaccinated. If it does have antibodies to the missing bit, it was likely infected.
Clever. What are they used for?
First developed for pseudorabies in pigs. Helped eradicate it in some places. Now used or being developed for bovine herpes virus, swine fever, avian flu, salmonella in pigs. Very useful for disease control.
A smart tool. Okay, let's step back into history. Before Jenner, there was variolation for smallpox.
Yes, deliberately exposing people to material from mild smallpox cases. Risky, but better than getting severe smallpox naturally. Practice in China, maybe from the 10th century, certainly by the 15th.
And it came to Europe.
Lady Mary Wortley Montagu brought the idea to Britain from Turkey around 1721. It gained some traction, even with royalty. But it wasn't safe. People could still get sick, die, or spread it. Prince Octavius died after inoculation.
Then came Jenner in 1796, the cowpox breakthrough.
Right. He noticed milkmaids who got mild cowpox didn't get smallpox. His famous experiment took cowpox pus from Sarah Nelms, gave it to James Phipps, later exposed Phipps to smallpox, and Phipps was protected.
And he called it vaccination.
Yes, from vacca, Latin for cow. He published in 1798, showed it was safer, could be transferred arm to arm. The Spanish used that method to take it to the Americas. Eventually, variolation was banned in England in 1840 because vaccination was clearly better.
Who came next? Pasteur.
Louis Pasteur, yeah. Developed second-gen vaccines in the 1880s, chicken cholera, anthrax, vaccination started becoming a national priority, then a big leap in production came with using chicken eggs to grow viruses, starting in the 1930s for things like yellow fever and flu.
But we use cell cultures more now.
Yes, since the late 1950s, cell culture became more standard for growing many vaccine viruses.
And the 20th century was the big boom.
Absolutely.
Yeah.
Diphtheria, measles, mumps, rubella, polio vaccines developed and rolled out. Polio vaccine was huge. And then the ultimate triumph, smallpox eradication, declared in 1980. Maurice Hilleman was a giant in the field, developed so many vaccines.
But some diseases still lack vaccines.
Sadly, yes. Herpes simplex, malaria, gonorrhea, HIV, still major challenges despite all the progress.
Could you quickly recap those vaccine generations again in this historical context?
Sure. First generation, whole organism, either live attenuated like smallpox, oral polio, strong immunity but tiny risks, or killed, no infection risk but maybe less broad immunity.
Okay.
Second generation, subunit vaccines, using just pieces like toxoids, tetanus, diphtheria, or recombinant proteins, hepatitis B, good antibody response, less cellular maybe.
Yeah, third generation.
The newer genetic ones.
Right.
RNA and DNA vaccines, Zika DNA trials, HIV DNA trials, and of course the mRNA COVID vaccines. Carrico and Weissman's work on mRNA was foundational there.
What are the current trends now, beyond just fighting infection?
Big push towards synthetic vaccines to potentially avoid resistance. Tailor-made vaccines for non-infectious diseases, cancer, autoimmune conditions, even high blood pressure experimentally. Using plants as vaccine factories is still explored. And then there's the challenge of
vaccine hesitancy.
Exactly. A major global health threat identified by WHO. We saw the impact with COVID-19, different uptake rates. It's defined as delaying or refusing vaccines despite availability. Ranges from uncertainty to outright refusal. And this is despite overwhelming scientific agreement on safety and effectiveness. It leads to preventable outbreaks and deaths.
A really significant social challenge layered on top of the science. Well, we have covered an immense amount of ground today, from the immune system's training to the long history, the types, the challenges.
It's a huge field.
For you, listening, who wanted that quick but thorough understanding, I really hope this deep dive gave you that shortcut, that clarity on vaccines.
Yeah, we've touched on the science, the safety, how they're made, licensed, scheduled, the economics. It really is a cornerstone of public health.
So thinking about everything we discussed, the history, the incredible science, but also these ongoing challenges like hesitancy and global access, what do you think is the next big hurdle we need to clear to really maximize the power of vaccination for global health? Something to ponder. Thanks for joining us on the deep dive.
Welcome to the deep dive. Today, we're tackling logic, really, the foundation of clear thinking.
That's right. It's fundamental.
You know how we always try to dig through all the information, find those crucial insights, the surprising bits, the aha moments that actually stick? That's exactly what we want to do with logic today. We've looked at, well, everything from academic texts to online resources like the Wikipedia entry.
Yeah, the goal is to cut through the complexity.
And give you a really solid grasp of this essential field.
Exactly. We want to show what logic really is, looking at, both the structured, formal side and how it actually works in everyday arguments.
Because it's not just for philosophers, is it?
Oh, definitely not. Understanding logic is relevant everywhere, in coding, making decisions, just navigating the information overload we all face.
Okay, let's start to unpack this then. At its heart, logic is, well, it's about figuring out what makes sense,
yeah,
right?
It's a good starting point.
We'll explore formal logic first, maybe. That sounds like the mathematical backbone.
It is, in a way. It deals with arguments where, look, if the starting points of the premises are true, the conclusion has to be true. It's purely based on the argument's form.
Like a kind of geometry of thought.
That's a neat way to put it. And then there's informal logic.
Right, that sounds more like real life.
Exactly. That's about how we actually argue, in normal, sometimes messy human language.
Okay.
That's where we look at things like misleading arguments, fallacies, and just critical thinking skills in general.
And you mentioned a logic can also mean something specific.
Yeah, just to add a layer, a logic can refer to a specific formal system, one with its own particular set of rules for proving things.
Interesting. So many layers already.
But what's fascinating is that all these sides of logic are really about analyzing arguments.
And an argument in logic isn't like yelling at each other.
No, definitely not. It's a structured set of statements. You have premises.
Oh, your points.
Right, the premises.
Yeah.
And they're intended to lead you logically to a conclusion. And these premises, the conclusion, they're propositions. Statements that can be either true or false.
And these propositions themselves have an inner life. Is that what you said?
Sort of, yeah. They have an internal structure, whether they're simple claims like the sky is blue or more complex ideas built up from simpler ones. We'll get into that.
So where did this whole idea even start? What's the origin story here?
Well, the word logic itself comes from the ancient Greek logos, which is just an incredibly rich word.
I've heard that. It means more than just logic, right?
But much more. Reason, yes, but also discourse, language, even the underlying order of things. Traditionally, logic was defined as the study of the laws of thought, or correct reasoning.
Correct reasoning.
Usually framed in terms of inferences, the mental act of drawing a conclusion, or arguments, which are how we express those inferences out loud.
Okay. So inference is the internal jump. The argument is showing your work.
Precisely. An argument, logically speaking, is just those premises offered up to support a particular conclusion. And the big question logic always asks is, does that support actually hold up? Do the premises genuinely lead to the conclusion?
And that question connects formal and informal logic.
It does. That's the shared goal, even if the methods are different. Though, historically, formal logic has often been seen as the main thing. Some logicians even equate logic entirely with that symbolic approach.
Okay, let's get into that then. Formal logic. What makes it formal? It does sound a bit imposing.
Think of it like taking an X-ray of an argument. Formal logic, or symbolic logic, uses symbols to strip away the specific topic.
Right.
So you can see the underlying logical structure, the skeleton. That's why it's so crucial in mathematical logic.
Because it doesn't matter if you're talking about apples or oranges, it's the pattern.
Exactly. It becomes topic neutral. The validity depends on the pattern, the form, not what it's about.
So instead of saying, if it rains, the street gets wet, you'd use symbols, like P and Q.
Precisely. If P, then Q. Formal logic is really focused on deductively valid arguments.
Deductively valid. Okay.
In these arguments, if the premises are true, the conclusion must be true. There's just no other possibility.
Yeah.
It's impossible for the premises to be true and the conclusion false.
Guaranteed.
Guaranteed by the form. This certainty comes from following specific rules of inference. Patterns of argument structure.
Can you give an example?
Sure. The classic one is modus ponens. It goes, premise 1, P is true. Premise 2, if P, then Q is true. Conclusion. Therefore, Q must be true.
Okay.
And that structure works no matter what P and Q actually stand for. It's a guaranteed logical link.
So it's all about these unbreakable logical chains based purely on the shape of the argument.
That's a really central idea, yes. Now, there's another way to think about formal logic, too.
Oh.
As the study of logical truth.
Logical truth.
Yeah, a proposition is logically true if its truth depends only on the logical words it uses, like and, or not, if, then. It's true in absolutely every possible scenario, regardless of what the non-logical parts mean. Think of either the door is open or the door is not open.
Right, that has to be true.
Exactly. It's true no matter what door we're talking about.
Yeah.
And these two concepts, deductive validity and logical truth, they're tightly linked. If an argument going from P to Q is deductively valid, then the statement, if P then Q, will itself be a logical truth.
Okay, that makes sense, but it still feels very abstract. How do we actually use this for a real argument someone makes?
Well, that's where translation comes in. You have to take the argument, which is usually in natural language like English, and translate it into a formal language, something like first-order logic. These languages have a very strict, limited vocabulary and precise rules, a syntax for how you build formulas.
Formulas, like logical sentences.
Exactly. Well-formed formulas. For example, Carmen is Mexican, and a teacher might become, say, MC.
Okay, so C is Carmen, M is Mexican, T is a teacher, and the wedge thing means and.
You got it. That's the and connective, yes.
Yeah.
It's like rebuilding the sentence with logical Lego bricks, as you said earlier.
Right. I like that analogy.
Once it's in that formal structure, then you can apply the precise rules of inference to check its validity.
So you can't just analyze my rant from yesterday directly with formal logic.
Probably not directly. You'd need that translation step first. And this leads to the idea that there isn't just one logic.
But many. You said a logic.
Exactly. A logic, technically, refers to a specific formal system. Different systems might accept different rules of inference or use slightly different formal languages.
So there are different brands of logic systems.
Kind of. Since the late 1800s, there's been a real proliferation, a big increase in these different formal systems. And funnily enough, logicians still debate what actually qualifies as a logic.
They argue about logic itself.
Sometimes, yes. For instance, some argue only systems that are logically complete, meaning they can prove all the logical truths expressible within them, like first-order logic should really count. Which raises questions about other systems, like higher-order logics.
That's brilliant. Okay, so if formal logic is about these precise abstract systems, let's switch to informal logic. That sounds like where the real-world messiness comes in.
You absolutely nailed it. Informal logic steps back from the symbols and looks at how we actually argue in everyday language.
Because formal logic struggles with that sometimes.
It can, yeah. Formal structures often have a hard time capturing all the nuances, the ambiguities, the context dependence of natural language arguments. Informal logic grew partly out of that difficulty.
Right.
It tackles issues formal logic might miss, but the core goal, it's still the same.
Assessing arguments, seeing if they're good or bad.
Exactly.
Yeah.
And identifying fallacies, those common reasoning errors.
So formal logic is the ideal playbook, maybe, and informal logic is watching the actual game, spotting fouls.
That's a really good way to think about it.
Yeah.
Now, finding one single precise definition for informal logic is tricky. It's more of a field with several overlapping ideas.
Okay.
One view is pretty straightforward. It just studies arguments as they appear in natural language, English, French, whatever.
Sure. As opposed to the formal translations.
Right. Formal logic analyzes the translations.
Yeah.
So an argument like, birds fly, Tweety is a bird, therefore Tweety flies. That's informal logic territory because it's just plain language.
Even though Tweety might be a penguin.
Exactly. That's a problem formal logic might not see easily, but informal logic dealing with content might pick up on. That's the challenge of natural language.
Ambiguity, vagueness.
Context dependence, all that. Now, a broader view sees informal logic as studying the standards of good argumentation itself. Rationality, critical thinking, even the psychology behind how we argue.
So not just the sentences, but does the argument actually make sense in the real world, considering everything?
Precisely. Does it hold up?
Okay.
Then there's another perspective. Informal logic focuses on non-deductive arguments.
The ones that aren't guaranteed.
Right. Where the premises make the conclusion likely, but not certain, unlike the absolute certainty aimed for informal deduction.
Like seeing loads of white swans and concluding all swans are white.
Perfect example. That's an inductive argument, a type of non-deductive reasoning often studied in informal logic.
So it's about plausible conclusions, even if we might be wrong sometimes.
Exactly. And one more view defines informal logic mainly as the study of informal fallacies.
The errors in reasoning.
Yeah, the ones that stem from the content or the context, not just the logical form, like attacking the person instead of their argument, the ad hominem fallacy.
Right.
And finally, some see it as formal logic deals with general patterns, informal looks at specific examples. So yeah, it's a diverse field.
It definitely sounds like it's trying to make good reasoning practical for the arguments we actually face every day.
That sums it up very well. Okay, should we move on to some of the basic building blocks, concepts that apply across the board?
Yes, let's get down to the fundamentals. What are the absolute key pieces?
Right at the core, you always have premises and conclusions. We've mentioned them a few
The
times.
start and the end point.
Exactly. And in a good argument, the premises provide support for that conclusion, like elephants are mammals and mammals are warm-blooded. Support. Elephants are warm-blooded.
Okay.
Now, these premises and conclusions, they are what we call truth bearers. They can be true or they can be false.
Makes sense.
In modern philosophy, the main view is that these truth bearers are either propositions, the abstract meaning behind a sentence, or maybe the sentences themselves, the actual words.
So the idea versus the specific wording, is there a difference?
Well, it matters philosophically. Focusing on propositions raises questions about these abstract meanings.
Yeah.
Focusing on sentences runs into problems with, say, ambiguous words or context. It's an ongoing discussion.
What about thoughts? Could they be premises?
That was an older idea called psychologism, seeing them as mental states. But it's not really the mainstream view today.
Okay, so arguments are built from these true-false units. What about inside them? Are they always simple?
No, they can be simple or complex. A complex proposition is built by linking simpler ones with logical connectives.
Like and, or, if, then.
Exactly those. A simple proposition doesn't have other propositions inside it, but it still has its own structure. It has parts like singular terms, that specific cat, and predicates is black.
Got it.
Now, the truth of a complex proposition, if it uses what we call truth-functional connectives, depends entirely on whether its simpler parts are true or false.
Okay.
For simple propositions like that cat is black, its truth depends on whether the term that cat and the predicate is black actually match up with reality. That's studied in theories of reference.
So the apple is red is true if the thing I'm calling the apple really is red.
Precisely. Now here's where it gets really neat. Some complex propositions are true no matter what.
Regardless of the parts.
Yes. In classical logic, something like either it is raining or it is not raining is always true. That's a logical truth.
Because it covers all possibilities.
Its truth depends only on the logical words, either or not. It holds true no matter how you interpret raining. Some philosophers even define logic itself as the study of these logical truths.
Statements that are true just by their structure.
You're definitely on the right track. And a fantastic tool for seeing how this works, how connectives function, is the truth table.
Ah, the grids with all the T's and F's. I remember those.
That's the one. Truth tables map it all out. Columns for the simple propositions, rows for every possible combination of true-false, often TF or 10.
Right.
And the table shows the resulting truth value for the complex proposition in each case. Like P and Q is only true in the one row where both P and Q are T.
Okay.
You can make tables for all the main connectives, not if, but, then, even less common ones. And you can build them for really complicated logical statements too.
So it's a visual way to check all the logical outcomes.
Exactly. A very powerful visual tool. And we've used arguments and inferences a lot.
Yeah, are they different?
Technically, yes, though often used interchangeably in logic talk. An argument is the set, premises plus conclusion. An inference is the actual process of reasoning, the mental leap from premises to conclusion. Arguments are judged correct or incorrect based on the support. Premises and conclusions are judged true or false based on reality.
Got it.
And in formal logic, there's the idea of a sound argument.
Sound.
It means the argument is logically correct, valid, and all its premises are actually true.
So a valid argument structure isn't enough for soundness. The starting points have to be true too.
Exactly right. Now, arguments can be simple, or they can be complex chains. You know, the conclusion of one step becomes a premise for the next.
Like building a case piece by piece.
Right. And for the whole chain to work, every single link has to be strong. And this strength of support varies. Deductive reasoning gives the strongest possible support.
The guaranteed kind.
Yes. Then you have ampliative or inductive reasoning, which offers weaker but still valuable support. Deduction is closely tied to formal logic. Ampliative reasoning often falls under informal logic.
Okay, let's dive deeper into those two. Deductive versus ampliative. What's the core difference again?
Okay, deductive validity. We touched on this. If the premises are true, the conclusion cannot be false.
Guaranteed.
Think, all squares are rectangles. This shape is a square. Therefore, this shape is a rectangle. If premises 1 and 2 are true, 3 must be.
Okay.
And crucially, validity is about this necessary link, not whether the statements are actually true about the world. An argument can be valid even with false premises.
Like the flying cats example.
Exactly. All cats can fly. Tweety is a cat, therefore Tweety can fly. The form is valid, even though the first premise is obviously false. The logic holds.
So deductive arguments are all about that airtight connection.
Precisely. Alfred Tarski, a famous logician, highlighted key features. They're formal, depend on form, a priori, don't need experience to verify the link, and modal, hold by logical necessity.
Right.
This formality connects to rules of inference, like modus ponens. If an argument structure follows these rules, it's valid. If not, it's invalid.
Right.
And deductive inferences are truth-preserving. True premises always lead to a true conclusion.
Does deduction actually tell us anything new, though, if the conclusion is sort of already in the premises?
That's a classic philosophical debate. In one sense, no deep new information is added. But deduction can make surface information, stuff that was implicit, explicit. Think of complex math proofs. The conclusion wasn't obvious, but it was logically contained in the axioms all along.
Okay, I see. So that's deductive certainty based on form. What about ampliative arguments? They amplify knowledge.
Exactly. Ampliative arguments are where the conclusion genuinely goes beyond the information given in the premises. This is where we often get new insights or knowledge.
But there's a catch, right?
There is. The premises make the conclusion probable, maybe even highly probable, but they don't guarantee it. It's possible for the premises to be true and the conclusion false.
So it's not guaranteed.
No. And this means knowledge from ampliative reasoning is often provisional. We might need to revise our conclusions based on new evidence. This happens all the time in science and everyday life.
Right.
Unlike deductive arguments, valid and invalid, ampliative arguments are judged on a scale strong or weak support. The line can be a bit blurrier.
So it's about making the most reasonable guess based on the evidence, but accepting you might be wrong.
That's a great way to put it. Now, terminology can be tricky here. Sometimes induction is used broadly for all non-deductive reasoning,
Okay.
but often induction is seen more narrowly as one type of ampliative argument alongside abduction.
So what's induction in the narrow sense?
Usually it means statistical generalization. You've observed a pattern in many cases.
Like the black ravens?
Exactly. See
Yeah.
thousands of black ravens, inductively conclude all ravens are black, or using a pattern to predict the next case. Every swan I've seen is white, so the next one probably will be too. Some philosophers stress that pure induction relies only on statistics.
Okay, and abduction, that's the Sherlock Holmes one, right? Inference to the best explanation.
Precisely. Abduction looks at evidence and asks, well, what's the best explanation for this being true?
Like the half-eaten sandwich on the desk example.
Yes. You see the sandwich, you infer the best explanation might be someone was here late working and got hungry. That conclusion explains the evidence.
But it has to be the best explanation available.
Crucially, yes. Well, the ones is likely. There could be other explanations. Maybe a raccoon got in, but the late-night worker might seem more plausible. The best fit for the facts.
Got it. Deductive, certainty, inform. Ampliative, new info, but probable. That's a really key distinction. So what about when arguments mess up? Fallacies.
You got it. Fallacies are arguments that fail to meet the standards of good reasoning.
It's not just about the conclusion being false.
No, crucially, it's about the reasoning being flawed. You could have true premises and even a true conclusion, but if the logical link is bad, it's fallacious, like the grass is green, therefore the earth is round. Both true, but the therefore is nonsense.
Right.
John Stuart Mill added an interesting point. He thought a true fallacy needs to appear correct on the surface. That's why they're persuasive, why people fall for them.
So they're like logical illusions tripping us.
That's a good way to think about it. Now, fallacies are usually split into two big types, formal and informal.
Formal fallacies are about the structure again.
Yes, an error in the logical form, like denying the antecedent. If P, then Q, not P, therefore not Q. That pattern is always invalid, no matter what P and Q are.
Okay.
But most fallacies we encounter daily are informal. The error is in the content or the context.
And there are loads of these.
Yeah, tons. They're often categorized into fallacies of ambiguity, unclear language, presumption, dodgy assumptions, or relevance. Premises just don't connect to the conclusion. We could spend hours just listing them.
Maybe another time. So we have rules for good reasoning. Fallacies break them. Are there different kinds of rules logicians think about?
Yes, there's often a distinction made between definitory rules and strategic rules.
Definitory and strategic.
Definitory rules are the basic rules of inference, especially in formal logic. They define what counts as a valid step. Fallacies violate these.
Like the rules of how chess pieces move.
Exactly. Strategic rules are more like chess strategy. They're about how to use the valid moves effectively to reach your goal, to construct a strong argument, to prove your point.
Ah, knowing the rules versus knowing how to play well.
Precisely. Some argue logicians should focus more on strategic rules to help people reason better in practice, not just spot errors.
That makes sense. Okay, we keep mentioning formal systems. What exactly makes up a formal system of logic?
Right. Think of a formal system as a carefully constructed logical mini-world. It typically has three parts: a formal language, axioms, and a proof system.
Language, axioms, proof system.
The formal language has an alphabet, basic symbols, and strict grammar rules, syntax, for building well-formed formulas, the sentences of the system.
Okay.
The axioms are starting points, statements accepted as true within the system without needing proof.
Like fundamental assumptions.
Exactly.
Yeah.
And the proof system gives you rules of inference to derive new formulas, conclusions, from axioms or other derived formulas. Some systems also include semantics rules for interpreting the symbols, often assigning truth values.
So you build this self-contained logical universe, starting with basic truths and using rules to find new ones inside it.
That's a great description. And the proof system's rules are purely syntactic. They work based on the shape of the formulas, not their meaning.
Like symbol manipulation.
Right. A rule might say, if you have P and Q, you can infer P. You apply these rules step by step to build formal proofs. There are different styles, like natural deduction or sequent calculi.
And the semantics adds the meaning back in.
Yes, it connects the language to interpretations, often truth values. Semantic entailment means a conclusion is true whenever its premises are true in that interpretation.
How do we know if a formal system is any good? What makes it work well?
Two crucial properties are soundness and completeness.
Soundness and completeness.
A system is sound if its proof system never lets you prove something that isn't semantically entailed. Basically, you can't prove falsehoods relative to its own semantics.
Okay, so it doesn't lead you astray.
Right. And completeness is the flip side. The proof system can derive everything that is semantically entailed. You can prove all the truths within the system's scope.
So sounding complete means provability and truth line up perfectly within the system.
Exactly. That's often the ideal. Now, shall we look at some of the actual systems of logic that people have developed over time?
Yes, definitely. Let's explore the different types.
Okay. For, wow, over 2 millennia, Aristotelian logic was basically logic in the West. But modern times have seen a huge expansion.
Right.
We can roughly categorize modern systems into classical logic, extended logics, and deviant logics.
Let's start with the big one, Aristotle. What was his main focus?
Aristotelian logic, though broad, is most famous for term logic, or syllogistics.
Syllogisms. I've heard of those.
Right. A syllogism is a specific argument structure. 2 premises, 1 conclusion. Each proposition has a subject, a predicate, and a copula, usually is or are.
Like Socrates is wise.
Perfect example. Socrates is the subject term. Wise is the predicate term.
Mm.
Unlike modern propositional logic, it doesn't focus on connecting whole propositions with and or.
It's more about how categories relate, like men and mortal.
Exactly. The famous square of opposition visually shows relationships between basic types of categorical statements. All S are P, no S are P, some S are P, some S are not P. Subjects could be universal, all dogs, particular some dogs, indefinite, a dog, or singular Fido. But it mainly dealt with simple properties, is brown, and struggled with relations, is bigger than.
Okay.
Syllogisms link premises and conclusion via a shared middle term. A huge part of Aristotle's work was classifying which syllogistic forms are valid and which aren't.
Based on the pattern of subjects, predicates, and quantifiers, like all or some.
Precisely. Valid. All mammals are animals, all dogs are mammals, therefore all dogs are animals.
Yeah.
Invalid. All dogs are animals, some animals are cats, therefore some dogs are cats. The form doesn't work in the second one.
Got it. That provides the historical base. How does classical logic compare?
Okay, classical logic is distinct from Aristotelian. It mainly means propositional logic and first-order logic.
The modern foundation.
Pretty much. It's classical because it relies on widely shared logical intuitions. Law of excluded middle, T or F, double negation, not P is P, principle of explosion, contradiction implies anything, bivalence, exactly one truth value.
Right.
It was initially geared towards math arguments, but it's used more broadly now. Still, its core focus means it lacks built-in ways to talk about things like necessity, obligation, time concepts, often handled by extended logics.
So classical logic is powerful, but maybe needs add-ons for some philosophical topic.
Exactly. Let's look at its 2 main parts. Propositional logic uses atomic propositions, P, Q, R, and connects them with and, or, if, then, etc.
Like PQQ.
Right. It treats whole propositions as basic units. It's great for showing relationships based on how complex statements are built, but it can't analyze inferences based on the internal structure of those propositions.
So it can't handle the logic inside all dogs bark.
Correct. For that, you need first-order logic. It includes all the propositional connectives, but also lets you talk about subjects, predicates, and quantifiers, some and all.
Ah, so you can break down the statements.
Yes. This raven is black, might be BR. Some things are black, could be BRSAX. First-order logic has rules for reasoning with these quantifiers and predicates.
That sounds much more expressive for talking about the world.
It is. Very powerful. Now, building on that, we have extended logics.
The add-ons you mentioned.
Exactly. They accept classical logic's core, but add new symbols and rules to reason about other areas, metaphysics, ethics, knowledge.
Like what?
Modal logic is a major one. It adds symbols for possibility, diamond, and necessity. Box.
So you can say, it is possible that P, or it is necessary that P.
Precisely. Means possibly P, P means necessarily P. And it adds new inference rules, like if something is necessary, it must also be possible.
Okay.
And there are different flavors. Deontic logic, for obligation, permission, and ethics. Temporal logic for time. Epistemic logic for knowledge, belief.
Wow, that opens up a lot of formal reasoning possibilities for philosophy.
It really does. Another type of extension is higher order logic.
how does that extend classical logic?
Instead of adding new operators, it allows quantification over predicates themselves, not just individuals.
So you can say there exists a property.
Exactly. Like, there exists some property F, such that Socrates has F. This gives huge expressive power, especially in math. But it comes with tricky metalogical baggage, so first-order logic often remains the standard.
Powerful but complex. Okay, now for the rebels. Deviant logics. What makes them deviant?
They reject one or more of those core classical intuitions we mentioned earlier. They're seen as rivals, proposing alternative ways to reason.
Okay, give us some examples. Who's deviating and how?
Intuitionistic logic is a big one. It uses the same symbols but ditches rules like double negation elimination, not P doesn't automatically equal P, and the law of excluded middle. P or not P isn't always accepted as true.
Why reject those?
It's often based on a view of truth as requiring constructive proof. You can't just assume something is true because assuming it's false leads to a contradiction. You need to build it. It's important in constructive mathematics.
So truth requires positive evidence, not just lack of negative evidence. That's a fundamental shift.
It is. Then you have multi-valued logics. They reject bivalence, the idea of only two truth values, true, false.
So more options.
Yes. Ternary logics might add an indeterminate value, useful in linguistics for vague statements. Fuzzy logics go even further, allowing infinite degrees of truth between 0 false and 1 true.
For dealing with fuzziness, like sort of tall.
Exactly. And finally, paraconsistent logics. These are designed to handle contradictions without exploding.
Exploding.
In classical logic, if you have a contradiction P and not P, you can logically derive absolutely anything, the principle of explosion. Paraconsistent logics block that inference. They're motivated sometimes by dialetheism, the idea that some contradictions might actually be true.
Wow. So deviant logics really question the absolute bedrock of classical thought. That's mind-bending. Now, what about informal logic? Can it be seen as a system too?
Well, it's generally less about building formal systems. It's more focused on analyzing real arguments, fallacies, specific contexts. But some frameworks do try to offer a more systematic approach to everyday reasoning.
Like what kind of frameworks?
One is the pragmatic or dialogical approach. It sees arguments as speech acts within a specific dialogue or context.
So the rules depend on the conversation.
Kinda, yeah. The standards for a good argument depend on the goals of that dialogue. Douglas Walton, for instance, views dialogue like a game with rules and goals. Arguments are moves. Correct moves advance the dialogue. Fallacies violate the rules, which might differ for a debate versus a negotiation.
So it's not just about the logic inside the argument, but how it functions in the interaction.
Precisely. Another angle is the epistemic approach.
Epistemic meaning related to knowledge.
Exactly. This focuses on how arguments help us gain or justify knowledge. A good argument should move us from justified beliefs to other justified beliefs.
So arguments are tools for learning.
Right. Fallacies, from this view, are failures in that knowledge-gaining process. Like begging the question, it uses the conclusion as a premise, so it provides no new justification. Logical rules are seen as norms for achieving epistemic success or rationality. The Bayesian approach fits here too, seeing reasoning as updating probabilities, degrees of belief.
That's very practical, judging arguments by whether they actually help us know things better. Okay, logic clearly isn't just theory. Where does all this research get applied?
Oh, everywhere. Logic tools are used in ethics, computer science, linguistics. And conversely, logic itself is studied using tools from math and philosophy. Research looks at applying logic, but also at its own foundations, assumptions, and properties.
What are some of the big research areas now?
Well, there's the philosophy of logic and philosophical logic. Philosophy of logic asks fundamental questions. What is logic? What are its limits, its assumptions? Philosophical logic uses logical tools, often extended or deviant logics, to tackle philosophical problems in metaphysics, ethics, epistemology.
Using logic to probe the big questions.
Exactly. Then there's metalogic.
Studying the logic systems themselves.
Yes. Investigating properties like provability, consistency, completeness, soundness, decidability. Can an algorithm decide truth? Expressive power. It uses mathematical methods to analyze the formal systems from the outside, looking at the relationship between syntax rules and semantics, meaning
like quality control for logical systems.
You could say that. Then there's mathematical logic, sometimes used interchangeably with formal logic, but more specifically, it's logic studied within mathematics.
How so?
It includes areas like model theory, interpretations of formal languages, proof theory, structure of proofs, set theory, foundations of math, and computability theory. What can algorithms compute? It explores math's foundations, leading to things like logicism, the attempt to base all math on logic, which hits snags like Russell's paradox and Gödel's theorems.
Right, the limits of formal systems.
Exactly. Set theory is still hugely important. Computability theory looks at algorithms, Turing machines, the limits of computation.
Which connects to computers.
Directly. That brings us to computational logic. It's the intersection of logic and computer science.
Building logic into machines.
Essentially, yes.
Yeah.
Implementing logical reasoning on computers.
Yeah.
Think automatic theorem provers, logic programming languages like Prolog. And conversely, logic is fundamental to computers. Shannon showed Boolean logic could model electrical circuits, the basis of digital computing, logic gates.
Wow, from abstract ideas to the chips in our phone.
It's a direct line. Then there's formal semantics of natural language.
Using logic to understand everyday language.
Yes, it's a mix of logic, linguistics, philosophy of language. It uses formal tools, often from model theory, to analyze meaning, usually linking it to truth conditions. It relies heavily on the principle of compositionality, meaning comes from parts and how they combine.
Trying to bring logical precision to messy human language.
That's the goal. Finally, there's the epistemology of logic.
How do we know logic is right?
Basically, yes. How do we justify rules like modus ponens? How do we know logical truths are true? Is it a priori knowledge, through reason alone, through understanding language conventions? Or, as some argue now, does it have an empirical basis?
Empirical, based on the world.
Some argue logical laws might reflect deep regularities in the universe, potentially even challengeable by science, like some interpretations of quantum mechanics questioning classical rules.
So even the certainty of logic itself is debated. Okay, let's wrap up with a quick look back. Where did all this start historically? It wasn't all invented recently, right?
Not at all. Logic developed independently in several ancient cultures. In the West, Aristotle is the giant. 4th century BCE Greece. Term logic, syllogisms.
A foundation for centuries.
Absolutely. He also touched on hypothetical reasoning, modal logic, induction. Hugely influential until the 19th century.
What about elsewhere?
In the Islamic Golden Age, logicians like Ibn Sina, Avicenna, were crucial. Avicennian logic built on Aristotle, but added much, influencing medieval Europe. He worked on propositional calculus, temporal modal logic, inductive methods. Fakhr al-Din al-Razi also critiqued Aristotle and developed inductive logic.
So important developments in the Islamic world, too.
Definitely. Medieval Europe then saw translations of Aristotle influenced by Islamic thinkers, people like Boethius, William of Ockham. And in China, schools like the Mohists and the School of Names debated language and reasoning. In India, Nyaya, Buddhist, and Jain traditions developed sophisticated logic tied to epistemology inference as a source of knowledge. The Navya Nyaya school had ideas remarkably similar to modern concepts.
It really is a global human endeavor trying to understand reasoning.
It is. The big shift to modern symbolic logic happened mid-19th century, spurred by questions about math's foundations. Frege's Begriffsschrift in 1879 is often seen as the turning point, though Leibniz, Boole, Peirce laid groundwork. Then Whitehead and Russell's Principia Mathematica in the early 20th century aimed to derive math from logic.
Introducing functions, quantifiers.
Yes, within rigorous formal languages. First-order logic became the standard, enabling formal math, set theory, model theory, modern mathematical logic.
A real revolution in precision and power.
Absolutely. So we've covered a huge amount today. We started with what logic is the study of correct reasoning. We contrasted formal and informal approaches.
Right, the symbolic versus the everyday.
We looked at core concepts. Premises, conclusions, truth, logical truth, truth tables. We distinguished deductive certainty from amplitude probability.
And talked about fallacies when reasoning goes wrong.
Exactly. We surveyed different systems, Aristotelian, classical, the extensions like modal logic, challenges from deviant logics, and even systematic approaches to informal logic.
Plus all the areas where logic is researched and applied today in its long history.
It's truly remarkable, isn't it?
Gah.
Logic isn't just some dusky academic topic. It's the bedrock of clear thinking, impacting almost everything we do.
And hopefully, for you listening, this deep dive has given you that clearer, more insightful grasp of the core ideas without getting bogged down. That was our goal anyway.
To provide that shortcut to understanding.
So here's a final thought to chew on. How can really understanding the structure of arguments, whether they look formal or just pop up in conversation, empower you? How can it make you a sharper consumer of information, a clearer communicator? Think about the arguments you run into every day: news, social media, work, family. How could applying some of these logical principles help you evaluate them better? Or build stronger arguments yourself.
Maybe something specific caught your ear today, fallacies, formal systems, maybe those weird deviant logics.
If so, we definitely encourage you to explore further. There's always more to learn. Thanks for taking this deep dive with us today. Welcome to the deep dive. You've brought us a source today that's definitely sparking some conversations, a Wikipedia deep dive on something called the enhanced games.
That's right. Yeah. We're looking at this pretty comprehensive Wikipedia article. It really lays out the basic idea, who's involved, and importantly, the reactions, which have been, well, intense.
Okay, so our mission for this deep dive, let's really try to unpack this. Where did it come from? What's the core argument? What's the pushback?
And crucially, what does this source actually tell us about where it stands now and if it could, actually become a thing?
Exactly. It feels like a dive into something pretty controversial that could genuinely challenge, well, how we view sports altogether.
Okay, so let's start with the concept, the big picture. The enhanced games proposed as an annual multi-sport event. Simple enough so far.
But the kicker.
The kicker, the defining feature, is allowing athletes to use performance-enhancing substances, PEDs.
Right. So that whole WADA system, the drug testing we see everywhere else?
Gone. Out. That's the core difference.
But interestingly, the source does point out it's not like you have to use them to compete.
No, exactly. It's an option, not a requirement. That's a key clarification in the article.
And it's not just drugs, right? The source mentioned other tech.
Yeah, things like advanced prosthetics, maybe certain shoe technologies too. Those are also explicitly allowed under this concept.
Okay, so if substances are allowed, are there any rules? Or is it just a free-for-all?
No, there are limits mentioned.
Hmm?
The founder stated that apparently for insurance reasons, only substances approved by the U.S. FDA, the Food and Drug Administration, would be permitted.
Ah, okay. FDA approval is the line.
Right. And the article specifically says things like cocaine and heroin are definitely out, prohibited. So it's performance enhancers, yes, but within that FDA-approved framework.
Got it. And how are they planning to group athletes, like men's and women's events?
Proposal mentioned in the source is to categorize athletes based on chromosomal sex.
Okay, so that's the idea. Ditch the drug bans, allow tech, follow FDA rules for substances categorized by chromosomes. Now, the timeline. Because the source suggests the plans have kind of shifted around a bit.
They definitely have. It was first announced back in June 2023. The initial list of sports was pretty broad track: swimming, weights, gymnastics, combat sports.
And the first event was supposed to be pretty soon, wasn't it?
Yeah, originally they were talking December 2024. And the founder, he initially threw out a number like maybe a couple of thousand athletes. Pretty ambitious.
So that changed.
It did. By August 2023, they'd scaled back that 2024 plan. Called it more of a smaller exhibition event.
Like a preview.
Sort of. And pushed the full event to 2025.
Okay, so 2024 became a soft launch, maybe. What's the latest from the source on dates and location?
Well, the most recent update mentioned in the article, that was from May 2025. Targets May 2026 for the full games.
2026, and the location?
Resorts World, Las Vegas, which is, a big step up from an earlier idea about maybe using a university campus.
Vegas. Okay, that signals something. And they've narrowed the sports for that first main event, too.
Yeah, for 2026, the focus is apparently on swimming, track and field, and weightlifting. Just those three to start.
It does feel like the plan is evolving, maybe based on, well, reality checks, funding, logistics.
Absolutely. The source mentions funding is key. While the founder later claimed, thousands were interested, picking a big venue like Resorts World suggests they're aiming for a specific scale, assuming the money comes through.
All right, let's get into the people then. Who's driving this? The main guy is the founder, Aaron D'Souza.
Right. Aaron D'Souza, Australian businessman based in London. He's the president. The article says the idea came to him after seeing steroid use in a U.S. gym.
And his reasons. The why behind it all. The source quotes him quite a bit.
Yeah, a big part of his argument, as quoted, is athlete autonomy, bodily freedom. He uses that phrase, my body, my choice, your body, your choice.
Applying that language here is interesting.
It is. And he pushes back against, governments or sports bodies telling adult athletes what they can or can't do, especially with things already approved by the FDA.
So it's framed as an individual rights issue. But he also seems to have major problems with the current sports establishment.
No, definitely. Very critical of the IOC, the International Olympic Committee, calls them corrupt, greedy.
And WA, the anti-doping agency.
He calls WADA an anti-science police force for the IOC. Pretty blunt. He also thinks the Olympics underpay athletes and have too many, quote, irrelevant sports.
So this isn't just about allowing PEDs. It's positioned as a fundamental challenge to the whole Olympic model. How does he envision the enhanced games operating differently then?
Well, he's quoted saying they can cut out all the waste, the bureaucracy, the big infrastructure builds, basically run it much leaner.
For virtually nothing, I think the quote was.
Yeah, and the idea is to use the profits to pay athletes better, invest in R&D for performance tech, and just build a bigger event over time. It's presented as this stripped-down, efficient, athlete-first alternative.
A disruptive model, essentially. The source also mentions his background a bit involved in that Belia versus Gawker case with Peter Thiel.
Yes, and co-founding a company called Sargon. It paints a picture of someone connected in tech and finance circles.
And interestingly, he says he's never used PEDs himself.
Yeah, the article notes that specifically.
Okay, so besides D'Souza, who else is involved, according to the source? Any other notable names early on?
It lists a few Olympians: Brett Fraser, Roland Showman, Christina Smith, and the geneticist George Church.
George Church, wow, okay.
And German billionaire Christian Angermayer is named as a co-founder.
So some serious backers. What about the funding? Where's the money actually coming from?
Well, they announced a multi-million-dollar investment round in January 2024. Venture capitalists, Peter Thiel again, Balaji Srinivasan, names often associated with, let's say, challenging established norms.
And there was another more recent investor announcement that caught some eyes?
Yes, February 2025. Donald Trump Jr.'s venture fund, 1789 Capital, got involved.
Okay. And the source includes his rationale. We should probably state that neutrally.
Right. The article quotes him saying, "The enhanced games represent the future, real competition, real freedom, and real records being smashed. This is about excellence, innovation, and American dominance on the world stage, something the MAGA movement is all about."
Okay, duly noted. So that adds another layer to the political and ideological dimensions here. Now, shifting back to athletes, James Magnuson, the swimmer, he became quite a focal point, didn't he?
He really did. Former Olympic medalist. Announced in Feb 2024 he was coming out of retirement, specifically for the enhanced games.
And the goal?
To break the 50-meter freestyle world record.
And DISA put up a big prize for that, right?
$1 million.
Yeah.
A huge incentive, publicly pledged. And Magnuson himself was very outspoken about it.
The source quotes him saying he does, what was the phrase?
Juice to the gills.
Yeah.
To break the record in 6 months. Very provocative language.
Definitely gets attention. What else did he say about why he was doing it?
Mentioned the money, obviously setting him up for a decade.
Yeah.
And he sort of framed sport as entertainment, maybe taken too seriously sometimes.
But he added a really important caveat, didn't he?
Crucial, yes. The source includes his disclaimer. This is not for everyone, and it is certainly not something for young athletes. That's a direct quote.
That feels significant to include. Did the source detail what he was actually taking?
It did. As of May 2025, Magnuson had stated he'd used testosterone, BTC 157, CGC 1295, ipamorelin, and thymosin. Pretty open about the regimen.
Okay, so you have Magnuson, the $1 million prize, his statements, the specific drugs. But then there was a twist with that record attempt.
A big twist. Just announced in May 2025, according to the source, another swimmer, Christian Gawolmeyev from Greece. He apparently broke the 50-meter freestyle world record unofficially at a private event back in April 2025, before the actual enhanced games.
Whoa, so he beat Magnuson to it and won the $1 million.
That's what the announcement, cited in the source, claims. His time was 20.89 seconds, just fractionally faster than the official record held by Cesar Cielo.
Wow, so the concept is already generating these kinds of high-stakes record attempts and payouts even before the main event, which I guess leads us right into the reactions. Because allowing PEDs, well, you'd expect strong opinions.
Oh, absolutely. And the source details a massive, mostly negative response, especially from the establishment.
Right. D'Souza and others claim lots of athlete interest, hundreds, maybe thousands contacting them, talk of sleeper athletes waiting.
Yeah, D'Souza mentioned potentially 500 sleeper athletes, even 2024 Olympians joining later. But the source also points out, like CNN observed early on, that very few athletes were actually going public with support.
And the media quickly coined a nickname, didn't they?
Steroid Olympics. Yeah, that tag popped up pretty fast and kind of set the tone for a lot of the coverage.
Okay, let's break down the reactions. Official bodies first. Overwhelmingly negative based on the source.
Completely. The IOC said it would destroy any concept of fair play, called it completely at odds with Olympic values.
National Olympic Committees.
Australia's called it dangerous and irresponsible. Sweden's ill-conceived, simply not sport. Very strong language.
And the anti-doping world. Predictable reaction there.
Entirely predictable. UK anti-doping. PEDs have no place in sport, nor the enhanced games.
USADA's chief, Travis Tygart.
He was quoted calling it a dangerous clown show, not real sport. Farcical, he said. World Athletics head Seb Coe basically dismissed it, saying nobody in athletics takes it seriously.
And WADA itself warned athletes.
Yeah, warned that just participating could lead to anti-doping rule violations under their code. So a clear stay-away message.
Okay, united front from officialdom. What about sports medicine groups, health organizations?
Similar concerns. Sports Medicine Australia said no support from their members as healthcare professionals. The Australian Sports Commission head said he couldn't imagine any responsible and ethical person thinking it was sensible.
Even the U.S. government weighed in.
Yeah, the ONDCP, the Office of National Drug Control Policy, stated the Biden administration had deep concerns, and the International Federation of Sports Medicine worried about exploiting young people.
So the main themes from institutions are safety, fairness, the definition of sport, and protecting athletes, especially young ones. What about individuals within sports? Athletes, former athletes? More mixed there, according to the source.
A bit more mixed, yeah, but still mostly critical or very cautious. You had cyclist Anna Meares calling it unfair, unsafe.
And Joseph Papp, another cyclist who'd served a doping ban.
He was pretty scathing. Said it invites recklessness, danger. Even referenced an old Saturday Night Live skit about athletes taking as many drugs as possible without actually dying.
Oof. Dark humor, maybe? Others?
Badminton player Susan Eaglestaff called it a massive danger. So lots of clear opposition focused on risk.
But there were some more, maybe nuanced takes. People who saw some angle, even if they wouldn't do it themselves.
There were. Swimmer Liesl Jones said she wouldn't compete because of the risks, but she admitted curiosity about performance limits.
And she raised an interesting side point.
Yeah, she wondered if it might, ironically, help clean up traditional sport by attracting those who want to dope. Like, if they go there, maybe mainstream sport gets cleaner. An interesting thought.
Anyone else?
Swimmers Libby Trickett and Mark Foster both kind of acknowledged the fascination, the money aspect, but they stressed hoping for medical supervision if people did participate.
Right. That medical supervision point keeps coming up. And one former Aussie rules player was actually a positive.
Adam Cooney, yeah. He found it enticing, thought lots of athletes would probably give it a go if they could.
Okay, so a spectrum, but weighted towards concern. How about scientists and academics, looking at it through their lens?
Safety was a big theme there, too. Andy Maya, a professor studying this stuff, called it a provocation. He specifically noted that the website materials he looked at didn't seem to address health risks adequately. No mention of medical oversight.
Wait, but didn't the source also quote D'Souza and Fraser saying supervision was planned? Clinical checks, screenings?
Ah, yes, you caught that. This is a really interesting point highlighted by the source. Mia criticizes the lack of info on the website he saw. But elsewhere, the article quotes Fraser saying supervision is mandatory and D'Souza talking about pre-competition blood tests, EKGs, the whole works.
So there's a disconnect. Or maybe the plans weren't fully publicized when Mia looked.
Could be either. Or maybe the plans are still being finalized. The source presents both the criticism and the organizers' stated intentions about safety measures. It definitely flags that as an area where the details seem, well, maybe not fully transparent or consistently communicated yet.
That's a really important nuance the source captures. What other academic viewpoints were mentioned?
Grigory Rodchenkov, the Russian whistleblower, he just called it a danger to health and sport, plain and simple.
Others.
John William Devine argued it would worsen inequality. Those with money get better enhancements. John Hoberman, who writes on doping, found D'Souza's whole concept scientifically simplistic and shallow.
But not all negative. There was one alternative view.
Yeah, Ronald Bailey, a science writer, he basically said, let the fans decide. If people want to watch enhanced athletes, let them. Shifted the focus to audience choice.
That's a totally different way of framing it as an entertainment product. Okay, finally, media reactions. Seems like a real mix there too, according to the source.
All over the map, really. Lots of skepticism and criticism. The Spectator argued sport needs natural advantage to be compelling. Cyclist magazine asked who would even sponsor this.
Concerns about viability and appeal.
Right. A Globe and Mail writer was curious but wouldn't want to be that athlete. Doubted top competitors would join. The Sydney Morning Herald. Dangerous, iniquitous concept. Straight criticism.
And specific critiques beyond just safety or fairness.
Yeah, Outsports took issue with D'Souza using LGBTQ plus terms like coming out for athletes admitting PED use, though they also noted D'Souza himself is gay.
Okay. But some media outlets seemed more intrigued, or saw it as a serious venture.
Definitely. The Daily Telegraph compared it favorably in terms of planning to the failed European Super League in soccer. Said it seemed more fleshed out.
Interesting comparison.
The Independent described D'Souza as intelligent and well-connected and deadly serious about making it happen. So acknowledging the potential, perhaps.
And some leaned into the spectacle aspect.
Yeah, Outkick's writer basically said, humans love watching incredible feats, modern gladiators, and PEDs for performance are fine in that context. Entertainment value.
The Financial Times
Called it a weird thought experiment, but conceded it could gain traction. And they noted, impartially, D'Souza's comment about a potential second Trump regime helping the games.
and the Times
Saw it as divisive, even dystopian,
Yeah.
but acknowledged D'Souza genuinely sees it as the future of sport.
It's clearly hitting a nerve, getting covered beyond just the sports pages.
Absolutely. The source mentions Time magazine included D'Souza and Angermeyer in their 2025 list of influential people in health. And The Economist linked it to the broader trend of human enhancement technologies.
So it's being seen as part of a larger societal shift, perhaps. There was even a docuseries planned.
Yeah, Ridley Scott's company and Rob McElhenney's production company were planning one. McElhenney was quoted saying it deserved a deep exploration. But the source notes those plans were later shelved.
Shelved. Okay. So bringing all this together from the source, what's the takeaway? This enhanced games concept, whether it happens exactly as planned or not, it's really forcing a conversation, isn't it?
It absolutely is. It throws a massive wrench into our standard ideas about sport, fairness, what natural even means, health risks versus personal choice.
And the future of human ability, really.
Exactly. It makes you, the listener, confront some fundamental questions. What do we truly value when we watch sports? Is it the struggle within perceived natural limits, the result of pure discipline?
Or is it seeing the absolute peak of human performance, regardless of how it's achieved? Pushing boundaries by any means necessary within certain safety rules they claim they'll have.
It draws a line, or maybe blurs a line, between human achievement and enhancement via science and tech. Where does sport fit on that continuum?
Yeah.
And, as that one academic perspective hinted, if enhancement tech keeps advancing, which it is, what does that mean for how we even define sport in the future?
Where do we draw that line between competitive fairness, as we've known it, and individual freedom or the pursuit of the ultimate performance? Definitely something to think about long after this deep dive ends.